Hello, this is Rohan-Paul. Very welcome to my machine learning and deep learning YouTube channel. Let's get started. Image matching is an important aspect of any computer vision project. Given two images, we need to know if they belong to the same scene or not. And this task is challenging, and the challenge arises from two aspects, which is geometric transformation of images, and other one is photometric transformation. So geometric transformation arises from translation, rotation, or scaling of images, and photometric transformation includes changes in the exposure or brightness of images. Consider these two images. This is a famous Indian architecture named Taj Mahal. So how can a computer know that these two images belong to the same scene? And the answer lies in finding good features in each images so they can be compared with each other. And one of the good feature of an image is its corner. And that's why in this video, I'm going to talk about one of the most popular and simplest corner detection algorithm called Harris corner detection. So what is a corner? 2 points. Corner is the intersection of two edges. The intersection of the two sides represent a point where the direction of these two sides changes. Therefore, the slope of the image has a high variation at the corner that can be used to detect it. And 2, corners are regions where differences occur between intensity. So if you look at this image, the first patch here, this square box, it's a flat region, no changes in all direction at all. Then look at this patch. This patch lies on this edge, so no changes along the edge direction. And now finally look at this patch. This patch resides on this corner, and we can obviously see that there are significant changes in all directions. Now, talking about features of an image, this first patch here, this square box, this cannot be any feature because there is no point of uniqueness in this patch. Now, the second one, which is on the edge of an image, this may be a feature, but even better feature is this corner. Why? Because compared to edges and flat surfaces, corners are translation invariant and rotation invariant, while distinguishable unlike edges, and of course unique. So what is translation invariance in computer vision? Take a look at this image. But first, generally in the world of computer, translation invariance means that the system produces exactly the same response regardless of how its input is shifted. So invariance means that you can recognize an object as an object even though when its appearance varies in some way. This is generally a good thing because it preserves the object's identity, category, etc. across changes in the specifics of the visual input, like relative positions of the viewer, camera, and the object. So in this image that you see on the screen right now, the image contains many views of the same statue. You and a well-trained neural network can recognize that the same object appears in every picture, even though the actual pixel values are quite different. So in the first, this is image, and then in the second and third row, it is there's rotation and the changes in the viewpoint, and then in the fourth row the size is different, and the fifth row the illumination of the exposure and the brightness is different. But in all these pictures is the same statue, and a neural network, well-trained neural network or a well-trained computer vision algorithm can recognize these changes, and that's what is translation invariance. And corners are translation invariant and also unique, which is what makes it such a beautiful feature of an image and is so important in computer vision. So finally, the topic of this video, which is Harris corner detection, and obviously there's a lot of mathematics behind this algorithm, but the key foundational concept is that corners are regions in the image with large variation in intensity in all the directions. So this is the basic 3 steps or the 3 steps or the 3 workflow steps of Harris corner detection. First, a fixed size window is made to slide throughout the image and find the window that produces huge intensity variation when moved in both X and Y direction. Then for each such window found, a score R is computed. And finally, the necessary corners are then selected by applying a threshold to the score. Generally, when R is small, the region is considered a flat region. When r is less than 0, the region is considered an edge, and when r is large, the region is considered a corner. And also, for a slightly more detailed view on the mathematics of Harris corner detection, I am taking a look at the OpenCV documentation itself. So, like I talked about, the key idea is to locate interest points where the surrounding neighborhood shows edges in more than one direction. So, mathematically, the basic idea of algorithm is to find the difference in intensity for a displacement of uv in all direction, which is expressed below in this equation. That is EUV equal to summation WXY, which is multiplied by these shifted intensity. So here E is the difference between the original and the moved window. U is the window's displacement in the X direction. V is the window's displacement in the Y direction. WXY is the window at position XY. This acts like a mask. I is the intensity of the image at position XY, and this expression, that is I x plus U and Y plus V, is the intensity of the moved window. The window function is either a rectangular window or a Gaussian window, which gives weights to pixels underneath. We have to maximize the term UV for corner detection, because remember, we have to find the areas of the image or the pixels of the image where there's a maximum differences in intensities after the shifted window function. So that means we have to maximize the second term here, and after applying the Taylor transform, final form of the equation becomes this, that is EUV equal to UV multiplied M, that is a matrix M, and matrix M is defined as this here, where IX and IY are image derivatives in X and Y directions respectively. And finally, this is the most important term, that this equation represent a score. The R is a score based on which it will be decided whether a particular patch is a corner or not. Now, in this final score function here, that is R equal to determinant of matrix M minus K multiplied by trace of matrix M squared. The K is a free parameter. It's like a hyperparameter and lets you influence the precision and recall of your prediction. So it means with a bigger K value, you will get less false corners, but you will also miss a lot of real corners. That is, you will achieve high precision. And with a smaller value of K, you will get a lot more corners. So you will miss less true corners, but will also get a lot of false ones. That is, you will have high recall. And normally the constant K is empirically determined in the range of between 0.04 and 0.06. And now finally, the code implementation using OpenCV. The entire Harris corner algorithm has been very well implemented in OpenCV's inbuilt function named corner Harris. So I'm just going to use it, and it will only be few lines of code, and you will have the corner detection algorithm applied on an image. In the first cell, I'm just importing the standard libraries, that is CV2, NumPy, Matplotlib, PIL, and then I already have a chessboard image in my local drive, so I'm just going to read it. Let's do my image equal to I think I have it chessboard. I'm just displaying the image that I just read. And this is my image, a simple chessboard. Now, before applying the corner Harris function, I have to convert my image to grayscale and also have the image array in float 32 NumPy format. So let's do these two steps. cv2.cvd color. The first parameter will be my image, and the second will be the conversion that I want to apply. So that will be this one. I think. Okay, let's check out CLOR color BGR to GR AY, this one. And so that's grayscale conversion, and I also have to have the have this image in float 32 format. So let's do that. Scaled equal to np dot float 32. Float 32 here, and image grayscaled. All right, and now I'm ready to apply corner Harris on this final variable. Let's do cv2 dot corner Harris, yes. And the first will be my, okay, here an important point on the parameters of corner Harris. So corner Harris function will take 4 parameters. The first one is the image, that is the input image. It should be grayscaled and float 32 type, which we have already done here in the first 2 lines here. And the second parameter will be block size. It is the size of neighborhood considered for corner detection. Third one will be k size. This is the aperture parameter of Sobel derivative used. And the last one, that is the fourth one, will be the free parameter k. This is Harris detector free parameter in the equation. We already discussed what k does for you. It will let you influence the recall and precision of your prediction. So now in the function corner Harris, I am supplying those parameter. The first one is my image grayscaled. Second one is the block size, and I'm choosing 2 here. And the third one is the k size, which is a Sobel kernel. So I'm giving 5 here. And the last one is the value of k. So let's give 0.1. And now let's see that what these returned. That is, just print this DST, the return value from the Harris corner. Let's run this cell. And after running this code, I get this array. It's a 2-dimensional array, which is what the Harris corner detector algorithm returned me. So cv2.corner Harris detector returns me a 2D array, the same size as the input with probabilities. Each position inside this array holds a confidence or the probabilities in this pixel being a corner. So to be precise, it is not the single pixel that is predicted to be a corner. It is a neighborhood that is centered at this coordinate. Now, before getting the corners, which is above a particular threshold of probabilities, I have to apply dilation to the image. So dilation is a technique where we expand the image. It adds a number of pixels to the boundaries of the objects in an image. Basically, it adds pixels to the corners of objects in an image to increase the object's area, and this is used to accentuate the feature. And the dilation step is primarily used for visualization, so you can see the corners better. So let's apply dilation. DST equal to cv2 dilate, and it takes the original image, input image. And the next one is the kernel. I'm not passing any kernels, so NE, and iteration I will give 2, itions equal to 2. And okay, dilation is done, and now I will be getting only the corners which is beyond a particular threshold value. So let's first write the code, and then I will explain. So let's do apply threshold. Get corners above threshold threshold. My image was my input image after obviously applying the grayscale conversion and converting to float 32. So let's my image DST 0.01 and I am getting the max values of DST. And setting it to 00255. So what this line is basically doing is that it finds any location in the Harris corner response map that it returns that exceeds the detection threshold and sets those location to this color. The color is defined as 00255. So basically, how this is working is that CV2.corner_Harris returns a value for confidence in its own prediction, and with DST greater than 0.01 then multiplied by DST.max, the code filters out the corners that are only low confidence and is only extracting the corners that are of high confidence. So only those corners will be marked as corner if the confidence is higher than 1% of the highest confidence. So DST.max will give me the highest confidence, and I want corners with 1% more confidence than this highest confidence. So now that I have applied the threshold with this line, I can actually print this my image after applying the Harris corner detector on it. So all the corners which are above this threshold will be marked with a particular color. The color has been defined to be this. But yeah, so let's do that. So let's plot that. So plt.figure pick size equal to, let's give 15. It's a square image. Axis of plt.show, that would be my image, and show. Let's also do the destroy all windows, which will clear any unused memory usage. If cv2.wetKey 0, and I have this written somewhere. 27, yeah, makes sense. Then cv2 dot destroy all windows. If any, what this will do is just, if any unrelated memory usage is not deallocated, calling destroy all windows will take care of that deallocation. It's just a good coding practice when you are working with OpenCV. Let's run this cell. Awesome. So this is the final resultant image that I get, and all these corners that is marked with this blue color, they are above the threshold that we defined earlier. So this is the final result. This is the corners that has been detected by this Harris corner detector algorithm. And that's pretty much applying Harris corner detection algorithm works with OpenCV. As you could see that there's only a few lines of code, maybe 4 or 5 lines. That's all you need to apply this whole algorithm. Now, another quick point I want to mention is now that I have got the final corners which are above the threshold that we have defined, how can we count the number of features, that is the number of corners detected as these dots identified as corner? To count that, I need to do the counting before applying the dilation. Remember, I applied dilation here, but dilation will this will do is this will add additional pixel around the borders of an object to make it more visible or to accentuate it. And that's why I have to, if I want to count the number of corners, I have to do the counting before this dilation step. So let's do that. And again, on this point, what is returned from the Harris corner detector in OpenCV function is a response map that gives you the probability that a particular pixel is a corner point. So here in this cell, I applied the corner Harris after converting my input image to grayscale and then getting to float 32, and then I applied corner Harris. And immediately after this, I have to do the counting of the corners on this DST variable before applying the dilation on this DST. So let's number of corners equal to, it will just be an np.sum dst greater than 0.01 multiplied by dst.max, because I'm getting only those that are 1% more than the highest confidence. Now you can just print them, number of corners, and that should give me the number of corners beyond this threshold, and in my case it's coming out to be 3679. Sorry, actually that is not 3679 because the this DST variable was already modified below, so I have to run the whole notebook from beginning. I can actually use this facility of VS Code execute above cells, and then I run this cells, and that will give me 575. So this is the number of corners above this threshold, and this is before applying the dilation. That pretty much wraps up this video. Stay tuned. My next few videos will all be on OpenCV, image processing, and computer vision. So if you have not subscribed yet, do subscribe. And if you have liked this video, smash the like button. See you in the next video.